between point masses, or charges, and uniform fields. Remember how we mentioned monopoles in an earlier mini-topic video? Well, these are what we imagine when we talk about point masses and point charges. Before we get on to talk about point masses and point charges, I just want to briefly talk about magnetic fields. You'll probably notice that we can't draw a magnetic field without two ends, a north and a south. This is different to electric fields and gravitational fields. You can have a single point producing a gravitational field, or a single point producing an electric field. For example, a star or a proton, respectively. These are monopoles, or single poles. But so far, we have never been able to find a magnetic monopole. Magnetic fields are what we call dipoles, so two poles. Electric fields can also be dipolar, so you could think of an electron and a proton a small space apart, but magnetic fields always exist this way. Why? Well, it seems to come down to a fundamental asymmetry in electromagnetism. Basically, there is such a thing as a unit charge, symbol Q, just as there is a unit mass, symbol M. But because moving charges create magnetic fields, there isn't such a thing that we know of that is a unit magnet. If you cut up a magnet over and over and over again, it would just make a lot of smaller magnets, each with their own north and south pole. We will cover more about magnetic fields around current-carrying wires and solenoids later in another mini-topic video. Let's kick the rest of this mini-topic video off by talking about arrows again. Yay! One thing you need to know in this course is the difference between a uniform and a non-uniform field. If you think about the word uniform, or of one form or shape, meaning the same everywhere, then you can probably anticipate what a uniform field would mean. If it's the same everywhere, then it's uniform. For example, this electric field between a positively and negatively charged plate is uniform, as is this magnetic field. A magnetic field due to a bar magnet is clearly not uniform. Is it the same everywhere? And neither is the electric field of a point charge, like this electron here. The quickest way to see this from the diagram is to look for the field lines. Parallel lines indicate uniform fields, whilst field lines which diverge or converge, that is, get further apart or closer together, are not uniform fields. Whilst we're on arrows, look closely at the variation in spacing between arrow lines far away from a point charge and close to the charge. Is there a relationship between the spacing of the lines and the strength of the field? Ah, what a smart cookie you are. Smaller spacing between field lines means a relatively stronger, more intense field. The general rule is true. If I have two masses, let's call them star 1 and star 2, and star 2 is twice as massive as star 1 but has the same radius, I would represent their relative gravitational fields like this. Lines closer together indicate a relatively stronger field. I'm very sorry for the boring star names. If you ever do go on to do anything in astronomy, I'm sure you'll be appalled, or perhaps impressed, by the creative thought processes behind naming some of the most famous surveys and telescopes. For example, the Very Large Telescope, VLT, the Very Large Array, VLA, and the Square Kilometre Array, SKA. It seems some people have tried to fix this situation, coming up with terms like GADZOOKS, GADZOOKS, exclamation mark. The gadolinium antineutrino detector zealously outperforming old Kamiokande Super! And FUC, which I will not be pronouncing today for your viewing pleasure, but which stands for the Far Ultraviolet Camera. You can look up more of these by searching for DOOFAS, DOOFAAS, or the Dumb or Overly Forced Astronomical Acronyms site, at your own leisure. Likewise, if I was looking at the uniform magnetic field between two magnetic plates and compared it to another similar setup, Could you tell which diagram represents the stronger magnetic field? As we'll cover in many topic videos later in the series, close to the Earth's surface, we model the gravitational field as uniform, even though when viewed from far away, we model it as a point source, a point mass, just like any other celestial body. In this area of study, you also need to know the difference between a static and a changing field. Static fields stay the same over time. Think 2 bar magnets just sitting there. A changing field varies over time. So if I started to move one of those magnets towards or away from the other, then the resultant field from the 2 magnets would absolutely be a changing field. Okay, so let's focus for this last bit back on point masses and point charges. I'm hoping that you'll actually be able to derive this rule for yourself. I know, crazy, right? If we have a proton here, hanging out in space, and just minding its own business, and I pop an electron at this point, let's call it R1. You can call it banana if you like, but generally I've found R for radius to be more helpful. There will be a force on the electron towards the proton, right? If instead the electron is at a distance R2, where R2 is 2 times R1, can you work out what the proportional force will be? Think about it like this. We're going to need to go into 3D. The proton has a certain amount of field goo. It gives it off from its surface. Can you see it's a spherical shell? At a distance R1, what space does that shell have to cover? General surface area of a sphere? Anyone? Cool, so 4 pi r squared. Now let's move to R2. Remember, R2 is 2 times the distance of R1. There's still the same amount of shell goo, but it's got to be stretched to cover the much larger space at R2. Now have a look at the maths. This comes out as 4 pi R2 squared. Remember how R2 equals 2 times R1? So compared to the point at R1, the goo is stretched over 4 times the space. The field gets weaker. We know this already. And we can see that it gets weaker by a factor of R squared. So field strength is proportional to 1 on R squared. This is the inverse square rule. It works for point charges, point masses, and actually quite a lot of things generally. We will unpack these formulae a bit more in upcoming mini topic videos. Here's an update to our summary table. You'll note that the field strength looks a bit more now how you probably expect it. The thing causing the field divided by the distance to the point we're examining this field. What's this capital G and small k, though? Well, the good news is that they are both constants. Basically, they represent the number link between the property and the field. But we'll discuss this in an upcoming mini topic video. This has been Red Lipped Astro. Point masses, point charges, and uniform fields. If you found this video helpful, please like and subscribe. Please also feel free to comment or ask questions below.